In this, in this video, I'm going to talk about the velocity equation and talk about some problems. Now, we talked in the last video, we talked about how velocity and speed are both rates of change of position. In other words, how much position changes by in a certain amount of time. And so we can make that a little more formal. In these videos, I'm referring to displacement as delta x. So the velocity is change in position, which is my displacement. I'll just write displacement up here, per unit time, delta x over t. Now there's one change I'm going to make here. First of all, we need to understand those are both vectors. I'm not going to use the notation because it'll get a little busy, but I'm going to put a line up here. And what that means is average. And that means that the average velocity over some period, during some period, is how far away you are from where you started divided by the time. Average velocity is displacement over time. And I'm going to talk a little bit about what that means. Speed, I kind of think of it as using the same equation. I mean, we're really using speed or velocity is rate of change of position. Change in position. And so velocity, that rate of change of position, it's really just change of position over time. For velocity, we use displacement. For speed, and I'll just abbreviate that speed, I never even use this equation, is instead of displacement, it's using distance over time. And I'll talk about the implications of that. So speed is distance over time, velocity is displacement over time. Whenever I'm doing a problem with speed, it's such a simple equation, such a simple concept, people seem to understand it pretty intuitively, that I just look at this equation. Average velocity is displacement over time, average speed is distance over time. Very few problems actually talk about that where you couldn't use the velocity equation. So let's take a look at what that means. Okay, velocity. I walk 5 meters in 2 seconds. 5 meters in 2 seconds, and I've got an arrow indicating where that is because I want to use displacement. My displacement is 5 meters, my time is 2 seconds, and so my velocity, average velocity, would be 5 meters in 2 seconds equals 2.5 meters per second. That's my average velocity. And in fact, it happens to be in that direction. One way I could make this better if I called this east. The displacement would be 5 meters east, and the velocity will be in the same direction as the displacement. It would be 2.5 meters per second east. Or I could define a frame of reference. I could call that the positive direction. And then my delta x, I don't even have to change anything. It's already positive 5. The velocity, positive 5 divided by 2, would be 2.5. You could see if I change that, and let me change a lot of stuff here, boom, 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 I'm going to get rid of that. I'm going to make the positive direction this way. That means my displacement would be negative, and when I take negative 5 and divide it by 2, the velocity automatically comes out in the right direction. It automatically comes, since I've called that positive, this is the negative direction, my velocity is in the negative direction. So picking a frame of reference and picking an assumed positive direction will help you an awful lot, particularly when we get to to acceleration problems. What about speed? Well, speed is distance divided by time. Well, the distance you traveled is 5 meters, the time is 2 seconds, and it's 2.5 meters per second. If you look, in this case, in the first case, when I called to the right positive, the velocity and the speed were the same thing. When I called to the left positive, now they're opposites. Speed is how fast, and I forgot to draw, this is average speed, 2.5 meters per second. So the speed and velocity, if the motion is all in the same direction and all in the positive direction, velocity and speed will be exactly the same. If, on the other hand, there's any change in direction, or if you're moving in the negative direction, the velocity will be different. Speed is a pretty simple concept. Let's take a look at a situation where the numbers themselves are different. In this case, what I'm going to have, I'm still going to go 5 meters, and I'm still going to take 2 seconds to do it. But I'm going to do it a little differently. So here, I'm going to say I walk 3 meters to the right, then I turn around and I walk 2 meters back. Okay, and let's call this positive direction, just to keep things simple. So my displacement from where I start to where I end up is 1 meter in the positive direction, right? I went 3 meters to the right, 2 meters back, so I end up 1 meter to the right. My time is 2 seconds. My velocity, average velocity, is going to be 1 meter divided by 2 seconds equals positive 0.5 meters per second. That's the velocity. And again, that positive sign indicates it's in the positive direction. My average speed, on the other hand, remember we use distance divided by time. Well, you traveled 3 and then you traveled another 2. That's 5 meters in 2 seconds. Your speed is still the same as it was in that first example I gave. It's 2.5 meters per second. So the average velocity and average speed differ, or can differ, when you have a change in direction. Okay, so just keep that in mind. Velocity is the one we tend to use. It's the more, I'll say, physicsy measurement. So that's the one we tend to use. When you get to acceleration, you really almost always use velocity. Speed is just, it's kind of a point of interest in some problems, but velocity is the thing that really ends up being the most important in these classes. Okay, now let me talk about something. We've got this average velocity, average speed. What does that mean? And the best way I can give an example of that is if I talk about going from DC to New York City. And you travel, oh my goodness, you got, let's just even talk, let's pretend it's a straight line. It's not. You're going to be driving over all sorts of different roads. But, you know, whether we talked about taking a car or taking a plane, the average velocity, let's say I drove and it was 250 miles in a straight line, and it took me 5 hours. My average velocity, sorry to write right across this, 250 miles per 5 hours is 50 miles per hour. But it's an average. That means it's the average velocity over that entire time frame. But if you've ever driven to New York City, you can average 50 miles an hour, but you pull out of your driveway. You're going 0 at the very beginning. You're going 0 anytime you stop for a red light. Maybe you stop for a light or a traffic jam multiple times. So sometimes you're going 0, sometimes you're going 60, sometimes you're going, well, you name any speed in between there. You're going all these different speeds. So the average velocity may be 50 miles an hour, but at a given instant, your instantaneous speed or velocity, oops, misspelled it, instantaneous velocity may be much more or much less than 50 miles an hour. So the instantaneous velocity is the velocity at 1 instant. If we're talking about a policeman has a radar gun on you as you go by, that's essentially the instantaneous velocity. This is how fast he was going when I pulled the trigger. Okay. And instantaneous velocity can be a little tricky, so I want to talk a little bit about how we measure it, what it means and how we measure it, and I guess it's more what it means. Let's take the case of a race. And this person is, boy, I hope I can draw this person, is all ready to run, and they're at the starting line of the race. And then the gun goes off, and they take off, and they are running. That's as good as I can do. And they take the tape. And let's say it's a 100-meter race, so delta x is 100 meters. And the time it takes them, they're very fast, 10 seconds. And the average velocity is 100 divided by 10 is 10 meters per second. So, but we know at the very beginning the velocity is 0. They start from rest. So to average 10 meters per second, they've got to kind of cancel that out somehow. So at some point they've got to be running faster than 10 meters per second. What generally happens in a race is you start slow, you get faster and faster. Depending on what kind of fatigue, you might even get tired at the end. So maybe your fastest would be right there in the middle. Well, how do we figure out how fast you're going right there or right here for that matter? What we need to do is to find the instantaneous velocity. You're really I guess if you had a radar gun, you could do that. But if we wanted to actually measure how fast this person is going there, we wouldn't use this total distance and this total time. We'd try to pull that in. We'd try to measure how fast they're going over a smaller time. So let's say you said, I'm going to have one observer here and one observer here. And we're going to find the time between those, and maybe you find the displacement. They're standing 10 meters apart. And the time they found was 0.8 seconds. Well, then they could find the average velocity. Average velocity will be 10 over 0.8. And that ends up being 12.5 meters per second. So you can see he was going faster. But look at that. That was over. This is still an average velocity. It's just a smaller time. This is closer to how fast he was going at that point. But it's not exactly how fast. He could have been going a little slower here or here. So the average might not be as fast as his fastest point. So to find that instantaneous, to measure the instantaneous, we'd actually have to make that smaller. Maybe we have our two observers there. Maybe we have our two observers there. Maybe we use a video and we can see when he was 1 inch before that, 1 inch after. Oh my gosh, listen to me using inches. I mean centimeters. 1 centimeter before and 1 centimeter after. Well, let's see what that would look like. If we did that, then maybe let's blow this up and magnify it. So here he traveled 2 centimeters, and I can't even guess how much time that would take. And you could use that. It's still an average velocity, but the difference is if you do it over a really, really, really small distance, then there's not going to be a whole lot of variation in the velocities when that runner was traveling 2 centimeters. Here's 2 centimeters with my fingers. Okay, so if you want to measure instantaneous velocity, you have to pick a really, really small time frame and a really, really small distance and use that. Now, if you're in the lab, you're measuring instantaneous velocities. That's how you do it. In most problems that we use, it's given. When we do acceleration problems, they'll just tell you, at the beginning he was going 0 meters per second. At the end of the race, he was going this much. It's a constant acceleration. You solve for acceleration. So that kind of problem, I don't want you stressing over that because in general you'll be given a velocity. Let's do one quick problem with that. Let's say I said a car was driving 30 meters per second. Okay, and let's say it's an average velocity. It's not changing. So average velocity is displacement over time. And we want to find out how far he'll go in 12 seconds. Well, what we do is we substitute our variables in. Average velocity is 30, time is 12 seconds, and we solve for delta x. If we multiply both sides by 12, 12 times 30, I'm going to leave out the units for now. And if we multiply both sides by 12, sorry about that, let me do it the way most people see algebra, 12 seconds. That cancels that, top and bottom. And this ends up being 12 seconds times 30 meters per second. The seconds will cancel, and you end up with 360 meters is your displacement. And that's a standard example of what kind of constant velocity problem. And notice I had to do that as an average or a constant velocity. simply because we haven't gotten to changes of velocity in equations yet. So that's how to solve a fairly straightforward velocity problem.